Why did this work instantly? All right. Finally got that going. That only took an extra 24 minutes. Holy crap. Can everyone hear me? I don't know why that didn't work. That was ridiculous. I have no... Oh, sorry. I'll turn down my input volume. I apologize. I have no idea whatsoever why that decided not to work. YouTube is horrendous, and I wish this wasn't the only platform, and I'm really sorry. Is that a better input volume for everybody? I just cut it in half. Hello, hello. Hang on, let's get a... Why are people leaving? We're going to do some math. Come on, I hope people are joining. Let's see. Going to do an Instagram story. All right, cool. I'm glad I sound good. There's only 3 of us. That's really annoying, but let's hope that ramps up over the next however long I have. I have to start work before like 1 o'clock. So let's wait until we get at least 10 people in the room. I hope that's not too much to ask. In the meantime, do any of the people that are in the room have any questions? Or I see a few names that I didn't see from last night. So I'm wondering if any of you saw the stream from last night. Live stream for... What do you want to do? What do I want to do? Well, I want to talk about things I'm going to do in the future of the channel. I want to just do some math on this board I have set up behind me. I wanted to, I don't know, share some of my collections of things, because I collect, like, well, my only collection is really my vinyl records, but, you know, books I'm reading, math I plan on doing, anything that, and if we get like enough critical mass of the people in here, I want people to just sort of like field me questions that they're curious about that I can do on this here board behind me, just for funsies, just for shits and giggles, you know? Oops, probably shouldn't swear. But once we get up to 10, hopefully my 901 subscribers will actually show up and not be fake fans. Let me just see here. I really hope Papa Flammy shows up. That'd be cool. Demonetized? Oh, because I swore. Yeah. Well. We're at 7 people now. Fake fans. Shake my head. Yeah, man. I agree. Completely fake fans. Really stupid. All right. 7 people now. He is kind of gay, though. Who's kind of gay? Papa? Pretty sure Papa's married to a woman. All right, we're at 8 now. Oops. Turn my sound off. Cool. We're at 8. We're at 8. This is such an exclusive... Tots, what's up with you? What do you mean? Who's kind of gay? Are you talking about me or are you talking about Papa? I assure you, neither of us are. Hello. 8 people now. Cool. I apologize for the delay. We're about a half an hour late. Because YouTube is awful. And for some reason, I can just start a stream. But if I have one scheduled, then it doesn't want to do it. So I don't know what to say to that. Well, of the 8, I mean, fuck it. Let's just get... Of the 8 people in the room, 9 people now. Do any of you have any, like... 10 people now. Cool. People are showing up. Finally. All right. 10 people now. 9 people now. All right. Y'all don't have any sort of sense of commitment. So, demonetization counter in 2. I love it. Okay. You know what we're going to do today? For the 7... Oh, Jesus Christ. Can't you people have an attention span of more than 5 minutes? God damn. I have 900 subscribers, not 900,000. There's not that many of you. What we're going to do today is we're going to answer a particular question, because I have this idea for a video, but I'm focus. But I'm introducing this idea to the people that are in the room now because God knows I want to do this. So we're going to answer a specific question right now. We're going to do when is an eclipse half over? Can everybody see that? When is an eclipse half over? I think that's a pretty interesting question. What does that mean mathematically? Well, we know that the moon, more or less from our perspective, travels at a constant speed across the sun, right, across the sky. Of course, we're talking about a solar eclipse. For me, this is appearing backwards, so I hope it is appearing in the right direction for everybody on the screen. When is an eclipse half over? Well, the obvious question is, since the obvious answer is when the moon, since the moon is traveling constantly across the sky, it's one more caveat. Because the moon going over the sun is just the mirror image of the moon going past the sun, the start of the eclipse is when the moon and the sun are tangent. Okay? That's the start of the eclipse. And the end of the eclipse is when the moon is entirely covering the sun. That's how I'm defining the start and end for the purposes of this question, okay? Because once the moon starts going past the sun, it's just all a mirror image of what we just saw. So I hope that's cool. The start is when they're tangential. The end is when the moon is completely covering the sun. And so, where's my eraser? Uh-oh. I need an eraser. Darn. There's one. So, hey, 11 people now. What a record. So, like I said, the start of the eclipse is when the moon is tangential to the sun, and the end of the thanks. And the end of the eclipse is when the moon completely covers the sun. So the obvious solution is in time, right? When is it half over in time? Well, we have the middle of the sun, and of course, the halfway point in time is going to be when the moon has just reached the middle of the sun, right? So it's gone one radius length of the sun. But that's not that interesting of a question because that's not that interesting of an answer because we can just sort of say, I mean, of course, okay, problem solved, right? It's when the moon is halfway across the sun. But what do we mean by halfway? That's the real question. Why wouldn't you put the end when the moon is tangent to the other sign? You're not done grocery shopping until you get back to yours. Yes, that's a good question. I did say before, because the moon going over the sun is just a mirror image in time of when it's going, when the moon gets past the sun, it's a mirror image in time to when it's going over the sun, right? You can just play that in reverse and flip the image, and it's identical to the moon going off of the sun. So it's sort of redundant is what I'm saying. So for the purposes of the definitions in this problem, we're saying that the start is when they're tangential and the end is when they're completely covered the sun. I hope that's fair because I'm not changing that definition. So live with it. So yeah, so this isn't a very interesting answer because it's in time and it's not, okay, we all know how to answer that question. Once you cover half the distance, you're done. But what about blocking half of the light? Right? What about blocking half of the light? Obviously, half the light of the sun, this is the sun, by the way, the sun and the moon. Perhaps I'll use different colors once I get down to the actual topic of discussion. When is the area of the sun half covered? Well, it's not right now, obviously, because I can draw a diameter that goes through that point there, and there's half the sun. Right? And there's these little extra bits, which means that this can't possibly be the point where... Oh, it's William. Hey, William. Hey, Bill, how you doing? That's my best friend right there. Yeah, so the half of the sun is clearly not covered, and so there's still more than half the sun. So the question comes, how far over does the moon have to travel for half of the sun to be covered, right? The And that's not an easy question. It's not difficult to answer, but it's not an obvious answer. Hello, Lavi Kolchinsky. Thank you for joining this stream of this very austere stream of 12 people. Integral time. Yes, we will be doing an integral. Yes. So, yes. So what we want to do is try to figure out how far along the sun, along the sun's diameter, we have to go for the moon to cover half the sun. Of course, this is a mathematical question, so we're making a few assumptions. The moon is traveling at a constant speed. The sun and the moon appear exactly the same size in the sky. And all of the light from all of the sun's disk is coming directly at us. So there's, I know this part of the sun is like curved away from us, so the light is going off in a weird direction. But let's assume for the sake of simplicity that it's all coming straight at us, so that when the moon covers half the area, it really is blocking half the light. Okay, so I hope that's okay. 13 people now. Ooh, we're a little unlucky. And so we want to answer the question, what fraction of the diameter? So the diameter of the sun will be 1, and time 0 is when the moon is tangent to the sun, and time 1 is when the moon covers the sun. So those are the assumptions, right? And it turns out that the diameter of the sun that you have to travel is not a nice number at all. And it's actually not even easy to answer in the context of the distance along the diameter. What you actually want to consider is the angle that you get when you do it, the central angle that you have from the sun center to the points of intersection of the moon overlapping. And once you start considering that angle, the answer becomes much easier to figure out. So now I'm going to exchange colors because we need something to represent the sun and something to represent the moon. So I'm going to stick with black for the moon, and I'm going to go with red for the sun because my orange markers don't hold up as well. I hope everything's clear so far, right? We're just going to figure out exactly how far along the moon has to go for it to cover the area, half the area of the sun, right? When is an eclipse half over? That's the question. So we need to do some math now. Finally, we do some math. So here's the sun. That bright red star that we're orbiting, right? And here's the center of the sun's disk. And we want to know when the moon is overlapping, right? Oh my God, guys, I'm black pen, red pen now. I'm black pen, red pen. When the moon is overlapping, oops, I guess that's what our moon looks like now, guys. When the moon is overlapping, what is the area of this weird eye shape in the middle, right? And when is it half? That's what we're trying to figure out. So what we want to do is we want to consider this angle here, this central angle that subtends the arc between the intersection points, right? That's what we want to do, and we're going to call that theta, okay? But usually, say the sun is the unit circle in this case, right? So we're on the xy plane, and this is 0, 0, right? And this is just a circle of radius 1 for simplicity. We don't really usually consider this total angle here sort of straddling the positive x-axis. We usually consider, right, this angle in here. So not theta, but theta over 2, right? So this whole angle here is still theta, which makes this angle in here theta over 2. I hope that's all right. So let's just make the moon a little more presentable. There we go. So how do we start using the angle to calculate the area? Well, we need to use trigonometry, right? That's pretty easy. Because what we want to do is we want to find the area of this eye-looking piece. It's called a, what we're going to end up doing is drawing this little dividing line. And we see that this shape in the middle is symmetric enough that we can break it up into these 4 equal pieces, right? Cool. And so as it turns out, we're going to calculate the area of one of these pieces. And then we're going to multiply that by 4, and that'll give us the area of the loon. Or no, that's not the loon. This is a loon, right? The crescent part is called a loon. This shape right here is called a circle section. I think it's called a section, right? And so we're going to calculate the area of this right here. And then we're just going to multiply it by 4. And that will be the definition of the area of the overlap. And we just want to find out when that's half, right? So what is it? So we're going to pretend that this is the unit circle, right? So that everything is normalized and everything's based around 1. And we have to figure out, we know that this point is 1 1, 0, right? Because that's the unit circle. So we need to figure out what that point is. And that's not very hard to figure out because it's just the cosine of theta over 2, right? This is the unit circle. So if this is the angle theta over 2, then this x distance here must be the cosine of theta over 2. And this must be the sine of theta over 2, right? That vertical spot there. Let's just see. It's called a sector if it's this whole thing here. If it's just the cap, if it's just the sphere, the circular cap, it's called a segment, I believe. I believe Nishita is correct. It's a segment. So actually, before we talk about the angle, let's just quickly naively see what happens if we try to attack it by using just x, the distance, just using the distance and not trying to consider the angle, right? Because we know that this is the unit circle. So this is x squared plus y squared equals 1. Right? In the xy plane, that's fine. And to get the upper half function, this part right here, we need to solve for y and take the positive case. So we'll get y is equal to the square root of 1 minus x squared, right? This function describes this right here, the top half of the sun. Yes, Flan is correct. Using distance does get complicated. So let's just see what happens first. So we're going to integrate this function from whatever this point is to that point there, which is 1. Right? We don't know what this point is yet. Let's ignore the fact that it's cosine of theta over 2. Let's just pretend we didn't think of that. And so we're going to integrate from x to 1 the square root of 1 minus t squared dt. You may be thinking, why did I switch from x to t? Well, this is called a dummy variable, right? The real function is with x right here, right? Hello, Nani. How you doing? Nani! I don't watch anime. I just know the meme. So we're going to try and integrate this and see what we get, right? This is going to turn out to be awful. But we actually know it's not just this, right? It's 1, 2, 3, 4 of them. So we actually have to multiply the integral by 4, right? Cool with that? So to integrate this, we need to be a little clever. We need to do a trigonometric substitution. So what we're going to do is we're going to let t equal the sine of theta, which means that dt is going to be the derivative of sine of theta, which is cosine of theta d theta, right? Cool with that? So we do our replacements, and we get, the whole board is visible. Good, good, good. This is a very wide angle camera. It's nice. William and I bought this to do live streaming, but that didn't really go anywhere. So we now have the integral, 4 times the integral. So we have to figure out what the bounds are going to be now, right? So we know... Wait a minute. No, let's ignore the bounds for now. Let's do the definite integral, the indefinite integral, and then plug in the inputs, because I really don't feel like doing the. Oh no, do we have to do it that way? We do, don't we? Okay, so let's just stick with the indefinite, the definite integral. So yeah, so we're going from x to 1 in the original one, but we now know that if t is x, then theta is going to have to be the arc sine of x, right? Because we have to invert and solve for the new bounds of the integral, right? So we have the 4 times the integral from the arc sine of x. The arc sine of t. My bad. And if t is 1, what does sine have to be? If t is 1, what does theta have to be for the sine of theta to be 1? Who can tell me? Pi over 2, that's correct. So pi over 2. And when we plug in sine of theta into here, we square it, and we get sine squared. And we get 1 minus sine squared, right? And 1 minus sine squared from the Pythagorean identity is cosine squared, right? And so, oh, everybody's participating. I love it. And so when we have the square root of cosine squared, we just get cosine, right? Cosine of theta. But we're also replacing dt with cosine of theta d theta. So we actually end up with an integral cosine squared of theta d theta, right? So this is a bit of a weird integral. Hello, the Doctor 123 Bow Ties Master. What a great name. Yep. So this is the integral that we need to try and solve now. How can we make this easier? Because integrating cosine squared is not very easy. So what we're going to do is it's not it's not immediately obvious, I'll say. It's something you do in like Calc 2 and it's fine. Let's erase this. And so what do we want to do? We know that cosine squared of theta plus sine squared of theta is equal to 1, right? But we also know, hello, Isaac, but we also know that cosine squared theta minus sine squared theta is equal to cosine of 2 theta, right? This is a Pythagorean identity, and this is the double angle formula for the cosine. And so we can actually solve for cosine squared in terms of cosine of 2 theta by simply adding these two things together, right? Because the sine squareds cancel, and we end up with 2 times the cosine squared of theta equals 1 plus cosine of 2 theta. Dividing by 2, we get a beautiful result. Hello, Simon, again. That the cosine squared of theta is equal to 1 plus 2 theta, 1 plus the cosine of 2 theta all over 2, right? So we're just going to replace the cosine squared of theta with this in the integral, okay? Hope that's cool. So we have the integral, 4 times the integral from inverse sine of x to pi over 2 of 1 plus cosine of 2 theta over 2 d theta. Naturally, the dividing by 2 can just be brought to the outside, and now the factor on the outside will just be 2, right? Because 4 divided by 2 is 2, right? That's not that bad. So now we can just integrate this thing term-wise, right? Because you're allowed to do that. Integrals are linear operators. So the integral of 1 is obviously just theta, because we're in the theta world. So we have 2 times theta. And then what's the integral of cosine of 2 theta? Well, we know that the integral of, or the antiderivative of cosine is sine. So the antiderivative of cosine of 2 theta is going to be something to do with sine of 2 theta. But because of that extra factor of 2, we have to divide by 2 as well, or else we get messed up, right? So, what was I going to do? So it actually comes out to be, what is it? It's plus, right? I'm not doing anything wrong, am I? It's plus sine of 2 theta over 2, right? That's the answer, isn't it? Yes, use the Chen Lu. Hello, Marion. How you doing? Now we have 21. Wow, record breaking. And so we're evaluating this from inverse sine of x to pi over 2. And so, of course, all we have to do is plug these things into these and then subtract after we've plugged this into there. Correct, Nani. It is 1/2 sine of 2 theta. That's what I put. So we plug in, how about we distribute the 2, right? So we're going to distribute the 2. That makes life a little bit easier, right? So we're going to plug in pi over 2. Pi over 2 times 2 is just pi, plus sine of 2 pi over 2, which is sine of pi, which is, of course, 0. So this term is 0 when we plug in pi over 2. And now we just have to plug in the inverse sines of x, and we end up with what do we end up with? We end up with, I feel like I've screwed up. I've made a mistake, I think. Or have I? Oh, no, I haven't. No. It's fine. It's fine. It is all good. So we have minus 2 times the sine of x, the inverse sine of x, minus sine of 2 times the inverse sine of x. Right? Well, this isn't very nice. Looks like we need the double angle identity, right? Correct. Very good. Whoever suggested that. That would be the double helix. Very good. Yes. So we need the double angle formula there. So we have pi minus 2 times the inverse sine of x. And now we're going to have minus 2 times the sine of the inverse sine. Well, that's just theta, right? Or I'm sorry, x. That's just x, right? Because we're taking the sine of the inverse sine. So we get x. And then we're going to be taking the cosine of the inverse sine, which if you do a bunch of basic trigonometry with like inverse sines and all that, you'll discover that that's actually the square root of 1 minus x squared, which is what we had before, right? Square root of 1 minus x squared. So this is the area formula from x to 1 of this right here. Very, very annoying, very cumbersome, not very nice. Yes, the answer should be, should it be a 1/2? No, it shouldn't be a 1/2 because before I had a 4, because there's 1, 2, 3, 4 area pieces. And so this integral calculated, you know, the area of all 4 pieces. And so that 1/2 factor that you're right about came out and canceled with the 4, and that's why we have a 2 here. So that's a good question, but that's why there's a 2 and not a 4 and a 1/2. But so everything's fine. This is the area function. It looks wacky when you plug it into Desmos. So what we need to do is we need to do a trig substitution, or not like a trig substitution so much as we need to sort of change the way we attack the problem. Because what I said before when we started was I need to put it in terms of theta over 2. So let's take a look at that. Let's erase all this now. The reason I'm doing this, by the way, is because the answer is ridiculous. It's an amazing answer. And it's sort of a number that's very obscure that most people don't know about. And so the 22 of you in here are going to get that as an exclusive. And I may end up releasing this as a video on its own too, once I've ironed out how I want to explain it, because clearly I'm a little rusty, because it has been a while. You know, the world has been falling apart. So let's look back at that original integral, right? We have 4 times the integral of x to 1 of the square root of 1 minus t squared dt. And we just discovered this horrendous formula. I am your 200th subscriber. Oh, hello. So we just discovered this horrendous formula for this area right here where the 2 circles overlap. But we don't want it to be horrendous. We want it to be nice and simple. And so that's what we're going to do. Because when we realize that this is theta, right, this full central angle here, and then cutting it in half, we get theta over 2, right? We want to put this in terms of the cosine of theta over 2, because that's what this distance is, right? And this is the sine of theta over 2. So this is the cosine of theta over 2. And so that right there, the coordinate for that point is the cosine of theta over 2. This point right there. So we're going to go from the cosine of theta over 2 to 1. So that's all we're going to do. We're just going to replace x with the cosine of theta over 2. And we're going to see if that really helps us. So let's I see people are arguing about who is my nth subscriber. You're all my nth subscribers, depending on what n is. And so all we're going to do is we're going to take that formula we just derived, and we're just going to plug this into it, right? And we're going to see that it's a beautiful simplification. So what we end up with is, what was the original equation that we just had? We had pi minus 2 times x times the square root of 1 minus x squared minus 2 times the inverse sine of x, right? That was the formula we just derived for the area of the I in the middle, right? And all we're going to do, because this was the x before, we're just going to take cosine of theta over 2 and plug it into this equation, okay? And so we get pi minus 2 times the cosine of theta over 2. And now we're plugging cosine of theta over 2 into here. So we're going to get cosine squared of theta over 2, and then 1 minus cosine squared of theta over 2. But we know what that is. That's sine squared of theta over 2 because of the Pythagorean identity. And we're taking the square root of sine squared. So we just get sine of theta over 2. Now, plugging that into here, we get minus 2 times the inverse sine of cosine of theta over 2. So this looks even more complicated, but I promise it will be beautiful. Because what is this? This is the double angle formula for the sine, right? Which means, because we know that, can everybody see what I'm writing up here? Cool. So we know that sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. If we just plug in theta over 2 for all of these things, we see that this expression here is just equal to sine of theta, which is a lovely simplification. So this is really just the sine of theta. So that got simple real quick. But it gets even better, because let's take a look at this abysmal thing right here. So the cosine of theta over 2 is a ratio of sides, right? Because it's trigonometry, triangle measurement. So if we take a look at some triangle, right? Of course, this is a right triangle. And this is 1, the hypotenuse is 1, and the adjacent side is the cosine of theta over 2, and this is theta over 2. Then what is the inverse sine of cosine of theta over 2? Well, the inverse sine is saying take the opposite side and hypotenuse of a right triangle and tell me the angle between them, right? But this is the adjacent side to theta over 2. So that isn't really helpful, right? We actually need to take our perspective to the other angle, because then, and only then, when we take the sine of this angle, we'll get cosine of theta over 2 over 1. Because now if we consider it from the perspective of this angle, this is the opposite side, which is what we need for the sine function, right? And this angle right here is pi over 2 minus theta over 2, right? Because theta over 2 plus this will give us pi over 2, plus pi over 2 gives pi. Yes, thank you. I try to look dashing and young, but I promise I'm but 23. Hello. So yeah. So now we've just derived that the inverse sine of cosine of theta over 2 is really just pi over 2 minus theta over 2. Right? It actually drastically simplifies. When you combine inverse sines, inverse trig functions and regular trig functions, they tend to cancel in really neat ways with roots and square roots and all that. But in this case, it's actually just pi over 2 minus theta over 2. And the beautiful thing is that all we have to do now is just replace that inverse sine with pi over 2 minus theta over 2, right? Where theta is this angle here, the full central angle that we had. But of course, the 2's and the 1/2's cancel. So we just get pi minus sine of theta minus pi, because negative 2 times pi over 2 is minus pi, plus theta. And we end up with the beautiful, beautiful equation. The beautiful, beautiful equation. Yes, I could have done that. That's a very good observation, double helix. But either way works. And we get the beautiful, beautiful formula that the area of this right here, in terms of this angle, theta, is exactly theta minus the sine of theta. And that's what we need. That's what we need. So now that actually gives us another formula. So this thing right here, this half of the eye shape, is actually called a section of the circle, right? Okay, Flan, whatever. Stop that. None of those lies. Come on now. Everybody's making the same joke. So you can just divide this by 2 and you get the area for a section of a circle in terms of the angle, right? Because the section of the circle is just this cap and the chord, right? But we want the area of this full thing here. Right? Now, this is where it gets really amazing. I promise. The approximation jokes, yes. Because what's the question? We want to know when the eclipse is half over. And we said that the obvious and uninteresting answer is when the moon goes halfway across the sun, because the moon moves at a constant rate, right? And so it's halfway across the sun, and then it completely covers the sun the same unit of time later. But the real cool answer is, when is the sun half covered? Well, this is a unit circle. So what's the area of this circle? Yes, the area is pi. So half of the circle will be when the area is pi over 2, right? And now we get the magic. So we want to know, when is theta minus sine theta equal to pi over 2? For what angle theta does that occur? And here's what we have to do. We have to move the sine over Actually, first what we're going to do is we're going to first what we're going to do is we're actually going to replace this. So we're going to use what did he say before? Double helix said before, and we're going to replace sine of x with cosine of pi over 2 minus theta, right? Because if you apply co-functions to complementary angles, you get the same number, right? Cosine and sine, they're complementary functions. So when you apply them to complementary angles, you get the same number. So I can just replace one with the other, and it's no problem. And of course, cosine doesn't care about negatives, right? It's an even function. It doesn't care about negative inputs. So we can actually just flip this difference. We can just flip that difference, and it doesn't change the value, right? Because cosine is even. And so now we're going to solve for this cosine term by adding it over and subtracting the pi over 2 over. And we end up with this neat-looking equation that if we want to find the theta that solves this equation, we get cosine of theta minus pi over 2 is equal to theta minus pi over 2. Now, what the hell is that? Sorry about the sun glare. Now, what the hell is that? That is a wicked result, because if we take a look at the cosine function and we ask ourselves, when is it equal to its input? Well, that would be if we have the line y equals x, and we ask ourselves, what's that number right there? It is correct, double helix. It is an attractive fixed point of the cosine function. And if you actually plug in any real number and cosine it again and again and again, it will always approach this number. It has no nice closed form. It is a transcendental number by the Lindemann-Weierstrass theorem, and it is called the Dottie number, named after my lovely grandmother. Not actually, but... So it is about, because it's on the line y equals x, the x and y coordinates are the same. So this number is about 0.739 ... And it's the unique real solution where the cosine is equal to its input, which means that since this is a real angle, right, it has to exist since this is a physical scenario, that this number, theta minus pi over 2, has to be, and we're going to call this capital D for Dottie. That was a horrible D. That means that this has to be equal to this number, this obscure number. And then when we solve for theta, we of course get that theta is just a 90-degree turn away from that. Theta is the Dottie number plus pi over 2, which comes out to be 2.30988 about. And what you end up with is this realization. So if we, or that, I mean, that is the realization, but it's, it means that the moon has to have this awkward angle going on here, where it's like this far along. Those are supposed to be circles of the same size. I know they look awful. I'm sorry. And this point, when this angle here, whoops, is 2.30988 radians, that is when this is equal to that. And that's the only point that it occurs. And that's a beautiful answer. It's this weird, obscure, transcendental number with a 90-degree turn after that, right? So if I sectioned off a 90-degree turn here, right? So this is 90 degrees. Then this has to be the Dottie number, right? Isn't that neat? Now, how long does it last? What do you mean? How long does an eclipse last? An eclipse lasts as long as it does. They can last anywhere between like a minute and 7 minutes, I believe. But this angle is independent of how long they last, right? The sun is covered once the angle, the central angle inside the sun with the two intersection points hits exactly this amount, the Dottie number plus pi over 2. is it will exactly cover half of the sun. So for that brief instant, it will be half covered. Now, this doesn't really answer the question in terms of what we originally wanted, though, right? I didn't ask based on the angle, right? I asked based on how far along the sun the moon has to go, right? The equality lasts for an instant, Marion, because the moon is always traveling. So it's. I mean, this is an irrational. This is a horrendously irrational number, probably. So it's an instant. I mean, it's not. Even if it were rational, it's only an instant in time, of course, because the moon is moving continuously. But again, we didn't really care about the angle. What I want to know is what fraction of the sun's diameter has been traversed by the moon, right? That's the, yes, but Marianne, you'll barely know. Every instant in time is an instant, right? Hello, Oily Macaroni, you finally joined us. Unfortunately, you're not a part of this discussion right now, like in this problem, but perhaps I'll do something involving your numerical value relatively soon. So actually, you know what's funny is the answer to this question is really close to the Oily Macaroni constant, right? Gotta call it by its right name. So you'll actually be pleasantly surprised, actually, even though it's not related, unfortunately. So we've just solved that the angle has to be exactly the dotty number plus pi over 2, right? But I don't want to know the angle. I want to know how far along the sun the moon had to travel, right? And Marion, this is exactly what's going to tell you when to do that, right? This answer right here. So it's good that you're thinking about that because this is how you do it. So we need to figure out exactly how far along the sun this is. I'm going to redraw this horrendous drawing. So, oh my God. So this black circle here is the sun. And this black circle here is the moon. So I know I haven't drawn it far enough over yet. But we're just going to solve the general case. Like, given the angle, how far along the sun has it traveled? That's the question. So this is theta. This whole thing is theta, which means that this is theta over 2, right? Which means that this distance here is the cosine of theta over 2, right? Because these are all unit circles. So I hope that's clear. This is the cosine. This is the cosine of theta over 2. And so I want to know how far this is, right? How far has the moon traveled across the sun so far? Well, we know that this distance is 1. And we know that this distance is 1 minus the cosine of theta over... Oh, that's the answer right there. Because this is 1 minus the cosine of theta over 2. This must be 2 times 1 minus the cosine of theta over 2. So to figure out the distance that we've traveled across the sun, we just have to plug our angle into this formula right here. So the distance is equal to 2 times 1 minus the cosine of theta over 2. And remember, theta is that wacky number we just derived. So, but as it turns out, this is going to tell you how many radius lengths you've traveled across the sun, because there are 2, right? Because the sun, if it's the unit circle, is 2 across. But we don't want that. I want it as a percentage, right? Something between 0 and 1. So what we're going to do to fix that is just divide by 2. So this is going to tell us, now d is for diameter instead of distance. This function, 1 minus the cosine of theta over 2, is going to tell us exactly how far along the sun we've traveled at that weird angle. So we plug in, so let theta equal the dotty number plus pi over 2, right? That was the number we just plugged in, which was about 2.3099988 or whatever. And we plug that in, and we get that the distance traveled across the sun once half of the area of the sun is covered, assuming that the distance across the sun is 1, we get approximately 0.596, which is quite close to the Oily Mascaroni constant, right? 0.596. So, Marion, if you wanted to figure out when you should take a picture of this, all you have to do is figure out when the eclipse starts, when it's going to end, take the difference between those times and multiply that amount of time by this number. And then apply that to whatever time zone you're in. And that'll tell you the exact moment in time when half the sun will be covered. And so what you can do to verify this result is exactly, Lobby. Yeah, exactly. So what you can do to sort of prove this to yourself is find any full video of an eclipse you can find and figure out when it starts, as in when is the moon tangent to the sun, and then figure out when it ends, as in when is it completely covering the sun. And then find out how much... Yay, Flammable Maths is here. Yes. Nice. Hello, Papa. So you missed a great demonstration. I hope I'll have it ironed out so that it's a lot less than 45 minutes. And I'll have this video out. It's very cool. It has to do with when is the moon half covering the sun. But yeah, so all you have to do, Marianne, is take a video of the eclipse, figure out when it starts and when it ends based on the definitions that I gave, and multiply the time by that number, and you'll find the exact moment in the video when the sun is half covered by the moon. So it's this factor, right? 0.596. So it's 59.5% of the way through the moon being tangent to the sun to covering the sun. So I hope that was clear. Was that a fun explanation, everybody? Did everybody enjoy that result? It's sort of something I figured out on my own, and I didn't look up anything for it. I just kind of... I actually had the answer 2.30988, like, as a numerical answer that I've known for a while, but I didn't have any closed form for it. And then when I took the sign of the number just to see if there was anything nice about it, and I got it as 0.739. But I remember, I'm not going to tell him to do things for me. But since Lavi suggested it, Papa, if you want to advertise this, I'd be so grateful for that. But the first 20-ish of you got a very lovely explanation about eclipses, and I will be making this into a video on its own at some point, just because it's a beautiful result, and I loved figuring it out. Let's take a look at something else. Does everybody still want to talk about math? Do you want to talk about books? Do you want to see what do you want to talk about? Does anybody have any questions about what I just explained? Sam right now took care of it. That's right, Bill. You should explain why D is an attractive fixed point. Okay, I don't actually have a good explanation as to why. I can sort of talk about it in a weird visual sense. So what does double helix mean when he says, or she says, attractive fixed point? They mean that no matter what answer or what input you plug into the cosine function, if you repeatedly... yes, I actually have a couple. If you repeatedly apply the cosine function, it will always approach this one real number, 0.739, right? The dotty number, as it's called. And why is it an attractive fixed point? Well, let's say we have the line y equals x, right? So this is our dotty number. Let's say I pick a point at random, right? This point right here. Or, I'm sorry, this x value that corresponds to that, right? So question, wherever you're doing research investigation like this, do you often make mistakes? Do you have to redo your work? Yeah, no, I make mistakes all the time. When you're sort of doing stuff that you don't know yet, or you haven't actually seen the conclusion, it's very easy to slip up and make errors. I spend a lot of time trying to iron out these things. The only reason this was rusty and took so long is because the stream sucked getting going, and I just haven't ironed out the explanation, but I've been working that sort of thing out for a while just to see if I could figure out the exact value, and I figured it out, right? It's the dotty number plus pi over 2. It's a lovely answer. So why is this an attractive fixed point? So I'm not going to explain why, because I don't actually have a mathematical understanding of why, but I can sort of show you with a little graphical intuition. So we apply the cosine to whatever this is, and that gives us that number right there, right? The cosine of that input x. Now, we want to treat this as a new input x that we're going to apply the cosine to again, right? So we have to figure out what x that is. And it's that x right there, right? You sort of just go across until you hit the x-axis or the y equals x again. And then you apply the cosine. And then you figure out when it hits the x-axis again. And I think you can see what's going on here. And then you apply the cosine, x-axis, cosine, x-axis, cosine. And you can see that it actually takes a really long time to converge once you get really close, but it just inevitably spins inward towards that. I have discovered what I believe is a fixed point, and it is the solution to the equation tan x equals... Hello, Jens, again. I'm doing all right. How are you doing? I hope everything's fine in Germany over there. I hope you're all staying safe. Where I just want to say, I know it's been a while. One of my videos that I haven't uploaded yet actually starts with me going, "Give Papa his channel back." But that's a little obsolete now, so I'll probably keep it and edit something on top of that. But I'm really happy you got your channel back. I'm loving all of your videos recently. Marian, something very similar can be used to find roots of numbers. This is just a numerical fact. This just happens with this function. Papa, I have a really cool response to your sum over the series of the sine of nt over n. And I'm going to rock your socks off. Just want you to know, it's a beautiful generalization. Not like a, it's sort of like, I would say it's more like a cool pattern to describe something that I feel like people have been thinking about for a little while. I remember Dr. Payam mentioning it once or twice when he was doing a couple videos on it. I won't talk about it right now because I actually had to order a new laptop because the one I'm filming this on right now doesn't even want to run iMovie anymore because it's just, you know, it's a few years old. I've spilled coffee on it once. So I had to get a new laptop. I'll probably just use this one for personal use until it breaks and just use the new one for only editing. But more videos to come. Once I get the new laptop, that'll be the day. That'll be the day that I start doing more videos. So it'll be here in, I think, about a week. So expect one more week of waiting, unfortunately. But I have lots of cool video ideas, and I can't wait to share them. Trusty Cup of Joe is dead. I just drank him all. I never really understand how much refining goes into these kinds of videos. It's good to know that I'm not the only one making. Well, of course, everybody makes mistakes. Everybody has those days. I never liked Hannah Montana. My cousin did. I think it has something to do with the Brouwer fixed point theorem, if you're interested. Isn't that the one where you say, like, if you shake a bunch of stuff up, there's always one thing left where it started? I don't know that that has anything to do with this. I'm simply ignorant of the fact. I don't know. So this is like a big sneak peek into videos that I'm going to be doing because I'm just sort of sharing stuff with you. What's this? Oh my God, Papa did share it. Is that the correct link though? Is that me right now? Well, it can also be intuitive. Let's see. Oh, it is me. Okay, this is the proper thing. Yeah. I'm seeing it on delay. I think about converging to a point. Okay. I don't know. I don't know the answer to the question, unfortunately. Same thing for sine, by the way. Sine has an attractive fixed point at 0. So if you apply the sine again and again and again to any answer, you're always going to get 0. So that's sort of the sine's Dottie number. Very much not as interesting as you know, the Dottie number. What's funny is somebody was able, in about 2004, I think, was able to prove that the Dottie number was equal to this really cool series over powers of pi. And I think it starts off something like this. So it's equal to pi over 4 minus, I think, pi cubed over 768, if I'm remembering these numbers correctly. And then the next one is, I think it's pi to the 5th over 61,440. And this just sort of keeps going, and you're just subtracting odd powers of pi. And this is this comes from the Lagrange inversion theorem of the like of a series for a function. So that's pretty cool. Does anybody have any specific math topics they want me to talk about while you're here? Anything you want me to cover? Anything you want me to continue doing? Anything at all? In that case, is there a maybe some more sneak peeks, graph theory? Yeah, I'm trying to interpret what Marion Gersa, I don't know. What Marion said. Is there a ration between parallel lines when it converges? What about some number theory? Oh, okay. What could we do with that? Oh, I have an idea. Surely I have some secret tricks. First of all, let's we just did some hardcore math. So let's do something nice and simple but very fun. I think it's fun. I'm going to pick a different color here. Let's do purple. So Papa, I just want to thank you again for promoting it. That was very kind of you to do that. But Euler's formula is kind of overdone. It's beautiful. It's always going to be the most beautiful thing in the world, mathematically speaking. I don't know how much more I have to say about it, though. But let's talk about angles inside of triangles. I'm going to show you 3 proofs of angles inside of triangles. So that the sum of the angles inside of a triangle is always 180 degrees. Nope, we're adults here. Pi radians, as black pen, red pen would say. We're adults here. We only use radians. So I'm going to prove in multiple different ways that the sum of the angles of any triangle, alpha plus beta plus gamma, is always exactly pi. I'm sorry, oily macaroni, that's not you. It's just some angle. Videos on the derivative of the gamma function. I believe I already did, didn't I? I did stuff on digamma, right? I did, yeah, I totally did. But there's more to talk about that. I'm totally happy to do more stuff on that. But I definitely did do videos on the digamma function, which is the logarithmic derivative of the gamma function. So what we're going to do is we're going to prove that the sum of the angles inside of this triangle in multiple different ways. Well, right now I'll do this once because then someone just asked me a really interesting question. That would be the Joker. So let's talk about this right here. Of course, there's the nice original proof that if you have 2 parallel lines and 2 points of the triangle of the base lie on that parallel line and the other point is allowed to freely roam, right? You get every sort of ratio of sides of the triangle, and I can also separate these parallel lines as much as I want. But the point is that this is a general argument, and so every triangle you see here has the same area. But the point is that the 3 angles always add up to 180 degrees or pi radians, and we can see that using internal angles, right, of these parallel lines, because we can treat these 2 sides of the triangle as transversals, right, as going through the parallel lines. So this angle is, of course, congruent to itself. This angle is, of course, by alternate interior angles, is congruent to this angle. And this angle here, also by alternate interior angles, is congruent to that one. And as you can see, these 3 angles in the triangle will always give you pi radians. So that's proof number 1. A little boring, a little blasé. How about finding roots of polynomials, proving that there's no general... Oh my god, okay, that requires like Galois theory, and I don't really feel like dying in a duel at the age of 20, even though I've past that point already. I can't believe I'm older than one of the most monumental mathematicians that ever lived. Because he died. Yeah, I don't have any desire to do that right now, because I simply don't know enough about it. I'm sorry. But this is a boring proof for the area, for the angles inside of a triangle. Boring. When is the Euler line of an arbitrary triangle? That is a great question. Wow. I have no idea. I have no idea how to even start with that question. When is the Euler line of an arbitrary triangle Well, it can't be an arbitrary triangle because the Euler line is not parallel to a side for an arbitrary triangle. It has to be a specific triangle. So you have to figure out when is it? What exact triangle is it when the Euler line is parallel to one of the sides? Very good question. I don't actually know. But here's a proof of the three angles inside of a triangle adding up to pi that I personally derived. This may have already been figured out, but I thought I want to come up with a new way to do it. Here's my way. So we actually have to start off with a quadrilateral with 4 right angles. Where opposite sides are the same. Now, I did not specifically say that this was a rectangle, right? I'm not going to try and assume anything, because what's the definition of a rectangle? A rectangle is a parallelogram with 4 right angles, right? So I have 4 right angles, and I'm assuming that the opposite sides are equal. From there, you can prove that these sides have to be parallel, which means that this is a rectangle, right? So no assumptions made. I start with the assumption, well, no unnecessary. So, right, I assume that the opposite sides are the same and that there's 4 right angles. Because I can then prove that the opposite sides must be parallel, that means that those original 2 assumptions will always give me a rectangle, which means that all rectangles have 1, 2, 3, 4 right angles in them, which all equal pi over 2, which means the angles at the very least inside of every rectangle add up to 2 pi, right? So we know that much. The sum of the angles in a rectangle is always 2 pi. I know we all know that the sum inside of angles of all quadrilaterals is 2 pi. But I'm not assuming anything I don't need to assume, right? So the only thing we know right now is that all angles in any rectangle will always add up to 2 pi, sorry. And we want to prove that the angles inside of any triangle will add up to pi. Why is that a focus? Come on. There we go. So first we have to prove that all right triangles have the audio is messing up. Hello? Can you hear me well? Is that okay? Something is up with the sound. The mic is going crazy. Is it better now? Mic. Nope. Any better? Hello. Hello. Okay, cool. All right. Maybe it's because I'm accidentally fiddling with the switch. I'll try to stop doing that. I'm a very fiddly person. So we just proved or showed very, very simply that every rectangle always has 2 pi radians in the sum of its angles. So if we now take a look at a right triangle, we know that that's a right angle, and that's pi over 2. We'll call this one delta, and this one epsilon. Right, so the first step to proving that all triangles have pi radians in all of its angles is we're just going to have to prove that right triangles do, just for part of the proof. That comes down to proving that delta plus epsilon has to be pi over 2. Right? Well, how do we do that? We take a copy of this right triangle, and we do this. We know that these have to be equal. And we know that because this is flat on the ground, and these are 2 vertical walls, that this has to be parallel with this, and this has to be parallel with that, which means we definitely have a rectangle, which means the sum of the total angles has to be 2 pi, and each corner has to be pi radians, or I'm sorry, pi over 2 radians, which means this has to be pi over 2, and this is epsilon right here, this is delta up here, and this is delta down here, and this is epsilon right there. So both of those have to be pi over 2, which means that delta plus epsilon equals pi over 2, right? So we just proved that the acute angles in a right triangle are complementary, which means that the total angles inside of a right triangle must be pi radians. So we've just proven it for the specific case of right triangles, right? Every right triangle has exactly pi radians in its angles. How do we use that fact to prove that in general for all triangles? It's quite easy. We actually need to utilize the fact that one angle is complementary to the other in a right triangle to do that, right? So if epsilon plus delta is pi over 2, then epsilon has to be the same thing as pi over 2 minus delta. I hope that's clear. And so what are we going to do? Now we need to answer the question in general, right? Let's answer the question in general. So we have an arbitrary triangle. It could be acute. It could be obtuse. We've already proven it for right triangles, so we don't have to assume that it's right or not right. And we're going to call this alpha. We're going to call this beta. And we're going to call this gamma, not the Euler macaroni constant. And since we've been able to prove that all right triangles have a total of pi radians in them, how can we break this up into two right triangles, right? Because then we'd be able to do it. And it's quite simple. If it's an obtuse triangle, by the way, you're going to want to lie the longest side flat like this, because otherwise what we're going to do is going to appear outside the triangle, and that's not very nice. So if this is obtuse, which it appears to be, I'm going to have the obtuse angle up here, and we're going to drop an altitude inside the triangle, which turns this arbitrary triangle into two right angles. Importantly, if this had been a right triangle, this still works, right? But it isn't, because we already proved it for right triangles. And now all we have to do is use the fact that we proved before about acute angles in right triangles being complementary, right? This has to be pi over 2 minus alpha, right? Because this is a right triangle. And this has to be pi over 2 minus gamma, which means that beta is equal to pi over 2 minus alpha plus pi over 2 minus gamma. That's what beta is. So if we add beta to alpha and gamma, you'll see that the gammas cancel and the alphas cancel, and we're left with pi over 2 plus pi over 2, which is precisely pi. And that's the original proof that I came up with for the sum of the angles inside of a triangle being exactly pi radians every time. This has probably been figured out before. I have no claim to it being completely my original, but I independently thought of it one day when I was just trying to do it myself. So I hope that was fun. But I saw a really interesting question before from my man, The Joker, who asked, try solving tan of x equals arc cosine of x. Oh, boy. Okay, let's just see what that looks like before I do that. I'm going to go to Desmos and graph both of them. I'm not going to cheat. I promise. Even if I recognize the number, I'm still going to say it could be different, and then I have to prove it. So what is it? Tan x arc cosine? Tan x and arc cosine. Oh, boy. That looks fun. What about when tan of x equals cosine of x? Is that somehow different? It's clearly a different number. So tan equals arc cosine. Okay. This is probably impossible. You're probably giving me a run for my money, right? You're probably yanking my chain. But let's see. So tan of x equals arc cosine of x. I'm just going to try things. I have no idea what I'm doing. Let's just make that clear. No clue what is going on at all. Why does it say double helix is the only participant left? What does that mean? Are we the only two here? You missed golden opportunity to say General Kenobi. Oh, sorry, Bill. So tan of x, if there's other people, it lies. Hello, Marion. Tan x equals arc cosine of x. So my first instinct is to, hello, everybody. Hello, getründelt? Getründelt! Ja, sehr gut. Guten Tag. Es ist ein schönes Tag. Ich weiß es nicht. So I'm going to take the cosine of both sides. So I get cosine of the tangent of x equals x. Tangent can be written as Oh, hang on, wait a minute. What if I do this? What if I do how have you because your name is Gertrundelt and I speak German a little bit. How else was I supposed to pronounce that? Getraundelt. No, it's Gertrundelt with the R in the back of your throat. I guess I'll square both sides. No, this can't be it. Oh man. Tangent of x equals arc cosine of x. Trundle is a League of Legends champion. Oh, okay. I wouldn't know. I don't play League. Well, there's always the famous adage that if two things are equal, then they must differ by 0. How does that help me? Well, I know that if I'm asking because I have not been able to solve it myself and can't find it. Yeah, well, if you go on Wolfram Alpha and type it in, it might give you a number. I don't know if it'll give you a closed form. Tan of x equals cosine has square root of phi as a solution or something similar. Oh. Well, square root of phi is 1.272, I think. Oh, no shit, Lavi. Of course. Sorry, I swore. If there's any children in here, I'm so sorry. That's a great idea. Let's start with that. Let's see what happens there. So we get sine of x over cosine of x is the tangent. Now, how about I multiply that over? So I get sine of x is equal to cosine of x times the arc cosine of x. Ooh, this is an integral that Black Pen, Red Pen did. Oh, remember he did sine times inverse sine and took the integral of that, and then I responded using this. So go check out that video if you want to see a cool integral, like an integral over this weird function. Let's see. If Wolfram Alpha isn't giving it a closed form, then I don't know how I'm going to find a closed form. But let's just see. Let's just see what happens. Is there like an arc sine identity where if you have the arc sine of a product, like that equals anything? Let's see. Let's see if there's an identity that I'm not remembering. Inverse trig identities. Let's see. Let's see. Inverse trigonometric identities. I want the arc sine of a product of things. Nothing. Doesn't seem to be anything. I'm not really sure that there is such a thing. I just got here. What the fuck is... We're trying to solve for x. If there's an x that satisfies that relationship. I can use complex numbers. Log y of x squared. Oh. But I don't know if that makes more complex. Yeah, I don't think this answer is going to be... I don't think this is going to be fun. Not that's not what I mean. I think it's interesting. I think it's a cool question, but I don't know that we can actually get a closed form expression for this. Let's find out. So tangent of x equals arc cosine of x. And we get the number. What do we get? We get 0.684745989563416. Not a very nice number, I gotta say. There doesn't appear to be a closed form expression for such a thing. I'm thinking this question might be a little impossible to answer in these timescales. Does anybody have any other questions? Anything you'd like me to cover? Yeah, I know we can make it a log function, but then that gets needlessly complex. Literally. 28. Wow. Record. What a record. Does anybody have anything they want me to do mathematically? Do you want me to talk about what I'm going to be doing in the future? Do you want to see my intense vinyl record collection? What do you want to see? That's not very mathematical, but, you know, I figured I'd ask. Usually it relates to fixed points we were talking about earlier. The solution is the fixed point you converge when applying arc cosine and arctan. Oh. Okay, prove the prime number theorem. God almighty. No. No, I'm not going to do that. What would be cool? What would be cool? Ooh, vinyl would be cool. Okay, I'll do that in a little while. Let's see. What's one more thing? So, do any of you know what the sophomore's dream is? Mr. S, what's your opinion on the infinite sum equals -1/12? What he's talking about is, of course, the infamous is quite a good word. So the idea that 1 plus 2 plus 3 plus 4 plus ... is somehow equal to -1/12. This comes from a mathematical trick that you do with this equation, but it's actually a false statement. This is not correct. You better believe that analytic continuation is worthy of your consideration, because it's quite literally what makes solving or understanding the function that gives us this result meaning, and it's what allows us to ask the most important question in pure mathematics, which is the Riemann hypothesis, which will help understand the distribution of primes as pretty much as good as we possibly can to within square root accuracy, as far as I understand that. I don't know enough about group theory to do that. I'm sorry. About finite fields and integral domains. I would love to know more about group theory. I simply don't know enough. Cesaro convergence. Well, that's when you take like the averages of the partial sums, right? I'm pretty sure Mathologer already did a video on that. Show the Goldbach. Show proof of the Goldbach conjecture. How you can do it. Yeah, I'll just test every even number and get back to you. Let's see. Let's quickly talk about that thing that I just mentioned before, quite quickly, real quick. It was I mentioned the sophomore's dream, right? The sophomore's dream. Let's talk about that, because that's a cool little demonstration, right? We got the integral from 0 to 1. I'm not going to demonstrate these. These are, Papa did a video on these. Check out Papa's videos. They're really good. We have these two amazing facts. And a lot of you are probably familiar with these, right? I am left-handed. Yeah, I met Mathologer. He's done cool stuff with maps. You've met him? Wow, that's really cool. I'd love to meet Mr. Polster. He seems like a fantastic individual. It's not supposed to be e to the x. It's supposed to be x to the x, right? These are transcendental functions that don't have nice closed form antiderivatives. So we have to evaluate only their definite derivatives, unfortunately. I'm sorry, definite integrals. And this one's really pretty, but this one isn't as interesting because x to the x pretty much does this. right, and shoots off to infinity and isn't very interesting. This, on the other hand, is the reciprocal of this and looks more like this and tapers off so quickly that the area under the whole curve is finite. So let's explore the rest of this curve. So as far as I can recall, this is about 1.29, I think, something like that. And so what's the rest of it? Let's go from 1 to infinity of x to the minus x dx. Now, I've already thought of finite. You just asked finite. Maybe you can create a function for coronavirus. They already are. They're called exponential functions. Or I'm sorry, logistic functions once they finally reach their inflection point. Hi, Cyrus. How you doing? Welcome back. From the previous stream, that is, the test stream. So let's explore the rest of this function, right? We know the area from 0 to 1 is this fancy schmancy sum. It's very beautiful. It's not a closed form, but it's about as good as you're going to get. Let's explore the rest of this. So we can make, we have the bounds from 1 to infinity. So there's a couple of functions that we know that sort of switch the inputs when we replace them if we're talking from 1 to infinity. We could do 1 over x, or we could do ln of x, right? So let's say we let x equal 1 over t. That tells me that dx is going to be negative 1 over t squared dt. And this bound up here is going to become 0, right? Because we plug in infinity into here, t has to be 0 in the limit, right? So this is going to be 0. And then plugging in 1 into there gives us 1 again. And we have 1 over t to the power of negative 1 over t times negative 1 over t squared dt. And now this can be simplified, interestingly, by using this negative to flip the bounds and writing 1 over t as t to the negative 1. So that becomes t to the power of 1 over t. And then we're dividing by t squared. So what we get is that this weird integral is actually an integral from 0 to 1 of t to the power of 1 over t minus 2. And so now we've turned this infinite integral into a finite one, which means you can approximate it to arbitrary precision, right? Yeah, so let's see if we can try and evaluate this at all. We can rewrite it a little. Let's see. Oh, there's another substitution we can make, by the way. I'm doing all right, Cyrus. It's a little warm in here. Should probably open a window. But we've been going. How long have we been going? For like an hour and 22 minutes. Okay. I have work at 1, so I'm gonna have to go at like 12:30. So we have like another 45 minutes about. So we can do another substitution that's actually going to bring this into the nice world of finite numbers. We can let x equal negative ln of u, which means that dx is equal to negative 1 over u du. And now the bounds become, well, how do we make x infinity here? We just have to plug in 0, right? Because ln of 0 is negative infinity, and then we're multiplying it by negative 1. So we have to plug in 0, and plugging in 1 gives us ln of 1, which is u has to be, oh no, I'm sorry. This is infinity, so u has to be 0. This is 1, so u has to be what? E to the negative 1, I think? Oh my God, it's Ababu. Is Papa Flammy still here? Wait, how do... Papa, your arch nemesis is here. That's so funny. Excuse me. Where's my trash? There it is. I hope Papa is. He's probably not still here. He probably has things to do. What do you mean by that, Ababu? Do you know that numbers have an end? Hang on, I gotta send. Let's see. Ooh, I have a new subscriber. Cool. Let's see if I have like multiple new subscribers. I have no idea. It's not divergent. The function is very, very quickly decreasing to 0 because it's the reciprocal of x to the x. So we get e to the -1 as that bound there, but then this negative is going to flip those bounds. So we have e to the -1 up top, and we have 0 down here, replacing x with negative ln of u and negative x with ln of u, and dividing by the reciprocal. We get another fantastic way of representing the area under the function. It's the integral from 0 to 1 over e of negative ln of u to the power of ln of u over u. So you're taking this, well, I appreciate you staying up, Pranay. I can imagine it's quite late where you are. Would that be India or Bangladesh or somewhere around there? Oh my God. Lavi, go to bed. I appreciate it, but damn. And as it turns out, if you actually consider this function from 0 to infinity, this integral becomes the integral from 0 to 1. So the integral from 0 to 1 of negative ln of u to the power of ln of u over u is equal to the full integral under this function, right? So the whole thing, which looks something like this. Let's move you all over a little bit. So, whoops, you're being turned. That's my room. We don't need that there anymore. So it looks something like this. Right, if you graph x to the negative x, you'll get this function here. And if you do a substitution to calculate the area under the function, you end up with this finite integral right here, the area under negative natural logarithm of u to the power of the natural logarithm of u, all divided by u. And it turns out that this exact area under the whole curve is about 1.995. Not quite 2, kind of annoying. I'd love to know what that I'd love to know what the hell that is. Do you have some determinant funny questions? I'm not really sure what you mean by that. Maths. I love your name, by the way. Somebody said before, do I have any math books? I have plenty. Let's see. I got a book on fractional calculus. So if you're interested in really fucking... Don't swear. Really messing your brain up. I can't bleep myself on the fly, so I have to stop myself from swearing. Fractional calculus. What is the half derivative? What is the half integral? What is the I derivative? Right? I have standard calculus. Analysis text. Complex analysis. I have a brief history of time. I know that's not strictly math, but it's Stephen Hawking. I have a book all about the number E, and to counteract that, I have the book that has not a single E in it. Not a single E at all. 50,000 words. So the word the does not appear. Any past tense with ed does not appear. Any plurals with es does not appear. Pretty amazing. Is the Abbott analysis book better than the Pew one? I don't actually know. I've never read the Pew book. Honestly, I find the Abbott book really quite enlightening. It, as the title says, helps me understand analysis, and I can't complain about it. It's the book I had for the class I took in 2017. I'm not reading all these books right now. I just have all of them. I went through the math books when I was in college. I haven't gone through them in a while. But I do have a lot of books to read. Let's see what's on my... Actually, screw it. Let's do this. Let's see what's on my list of reading. So right now I'm reading Edward Snowden's biography. The Abbott book is good. Enjoy it. This is a great book if you want to know how all of your rights are being taken away, if you're in America, / having already been taken away. I Am Legend. This is like the only fiction book in my to-read list, so that's coming up next. You may have very quickly seen that painting right there, which is Alex Gray-inspired art, because I'm a big fan of Alex Gray and the various Maynard James Keenan bands, like Tool and A Perfect Circle, which is why I have to read his autobiography next. Very much looking forward to this. Speaking of math books, I have Zermelo's Axiom of Choice. This is a very dense book to try and get through. I've tried my best. It's not very easy to read. Set theory is, believe it or not, really dense. So I'm doing my best on that. For my birthday, my brother's friend's girlfriend got me this book, The Strange and Infinite World of Numbers. Am I still a student? No, I graduated last May. I'm not a student anymore. I wish I was. Being a math major was fantastic. I reject the getrundelt. Well, you can or you can't. It's all still consistent whether you have it or not. I've got my brother's girlfriend got me this book, Pop Science. It's a fun little book filled with facts. I have Carl Sagan's book, The Dragons of Eden. I got to read that. And I have Stanislav Ulam's Adventures of a Mathematician, so I have to read that too. Pure or applied? Well, no, I just did a math major. I should have done computer science minor or double majored, but it's the choices we make, right? Maybe with this crisis, I'll end up going back to school or something. Perhaps I'll just become an electrician. Who knows? And I also have this enormous tome to read. Charles Darwin's set of works. So it's got The Adventures of the SS Beagle, or On the Origin of Species, and two other books. Hang on. It's huge. So it has The Voyage of the Beagle, On the Origin of Species, The Descent of Man, and the Expression of Emotions in Man and Animals. I find biology very interesting, especially evolution by natural selection, so I'm very much looking forward to getting into this. I only got it 2 Christmases ago, and I haven't touched it yet because I have such a long reading list, and I don't read slowly, but I take breaks between reading that are kind of extensive. I have to tell Papa Flammy that his mortal enemy is here. Your mortal enemy is here, spreading lies. Quote, numbers have an end. Yes, very interesting indeed. I can't wait to get into it. What else? That's really all the books that I have on my reading list. Do I have Goodreads? I like your book collection. I don't know what Goodreads is, actually. I've never heard of it. I have to put all these books back now because I've made a mess. I know this has kind of devolved into just a conversation, but I appreciate that. Oh my God, is he like legitimately a finitist, or is he just trolling? I really hope he's just trolling. But I don't know if he's, or that person specifically is just making up. Oh, I also have this book, Lend It to Me, by a lovely lady. Let's see. Do you happen to listen to classical music? If not, what music do you like? I don't really listen to a lot of classical because I'm not very much into it, but there's some cool there is some cool classical music. I really like, what's his name? I say I really like him and then I can't remember his name. I can't remember. There's so much music. But if you want to know what music I like, how about we take this to less math and talk about music. So someone mentioned that they wanted to actually see my extensive vinyl collection. Orff is cool. Vivaldi's cool. Sorry, you just had to look at my crotch there for a second. So I'm going to bring you all over here. You get a view of my room. So yeah, this is a cool painting that I have. That when I started college, my girlfriend at the time painted it for me. But I mean, it's a beautiful piece of art. I'm not going to give it up. It's lovely. And it's inspired by this album over here. Hang on. like science fiction. I'm not a big fiction guy, honestly. I like nonfiction a lot more. That's the Pink Floyd picture, the promotional picture, and that's a 1,000-piece puzzle that I did with my best friend in my junior year of college. It was a fantastic puzzle to try and solve. But that painting is inspired by this album, 10,000 Days by Tool. Big Tool fan. So that answers your question. My main band would be Tool. I do love me some Tool. And it doesn't stop. I got all the Tool CDs, big fan. The bassist for Tool is one of my main inspirations for my style of bass playing. The other would be the only other band that I have CDs for, and that would be the band... Where are you? That would be the band Mudvayne. Now, I'm a big metal fan as well. I have not listened to Owl City. But the bassist for this band is absolutely bonkers. And he is, not him personally, he's a lovely guy, according to all the interviews that I've seen. But he's an amazing bassist. And so I have all the Mudvayne albums too. All the Mudvayne albums. All of them. Even some singles and some bootlegs in the back there. So, yeah. So those are my CDs. But who cares about CDs? Let's talk about vinyls. Let's talk about vinyls. So this is a small little box I have right here. This is clearly the much bigger box. I hope that you contribute to spreading the theory of numbers have an end if you want to be a blessed person and really praise him, Ababu, praise you. Unfortunately won't because infinite sets exist. So I unfortunately can't do that. I can't abide by such a false statement. So if we're curious about vinyls, I have a bunch of Queens of the Stone Age albums. I'll just show you my favorites. So these are the Queens of this. I have a couple more Queens albums as well. I have both Royal Blood albums. What else do I have? I have this was my mother's vinyl. This is a great record. Moonflower by Santana. Oh my goodness, these things are unwieldy and large and hard to deal with. But I can do it. We have, of course, the Shins. The Shins. We have a national favorite, Simon and Garfunkel. If Bill, I don't think Bill is still here anymore, but he's the one that gave this to me. We have the All-American classic, Doggy Style by Snoop Dogg. Oh, yeah. Got some Sublime albums. Got some Tame Impala. Right, you can see the other Tame Impala album that I have. It's right there on the front. That's Lonerism. I have the one thing that John Paul Jones and Joshua Homme and Dave Grohl did together, them Crooked Vultures. Really, really brilliant album. I love it. It's a great album. Naturally, as the Tool fan that I am, I have all the Tool albums that I can get. Opiate, Lateralis, and Undertow. Right? I have Scum Beep Flower Boy by Tyler, the Creator. Great album. Great album. A couple oldies. We have Band on the Run by Wings. That's that would be Paul McCartney, right? And his wife at the time. I don't know if they're still married. Linda McCartney, right? And of course, their other awesome album, Venus and Mars. Fantastic albums. And I have another entire box of stuff right there. I don't really feel like going through all of it, so I can just pick out like a favorite or something. Oh yeah, my brother's girlfriend got me this record. If you want to hear, you mentioned someone mentioned classical music before. If you want to hear some of the coolest instrumental music of your life, check this band out. They're called Go Go Penguin. It's very, very cool. I won't say what I was doing the first time I heard this because it's probably a little contentious, but it was more or less a religious experience hearing this music for the first time in the context that I did. So I cannot recommend, especially this album, enough. It's really something else. And the best for you have a t-shirt about the theory of numbers have an end. Yeah, well, I'm pretty sure Papa is the one that made something like that. Close. But I won't go any farther than that. Ever heard of the Alabama Shakes? They're a great band. And this record is pink and blue. It's pink and blue. Obviously pi, because tau is a construct. Tau is a construct of your imagination. It isn't real. I'm a big fan of Arctic Monkeys. I have every Arctic Monkeys album. Whoops. I have every Arctic Monkeys album. Even who the are Arctic Monkeys. I'm just joking. It's not. Pi is just convention. Go Go Penguin sounds like a kid's show. It does sound like a kid's show, but it's an amazing jazz band from Manchester, England. I think I'm done showing records now. That sort of loses